Welcome to Physics 30 Prep Fast Track. We're talking about gravity, and then we'll look at some examples of these kinematic problems, and we'll practice them. So, of course, Isaac Newton didn't invent gravity, but he did discover the relationship gravity applies throughout the universe. What he said was that two masses are attracted to each other by an unseen force. That force is called gravity. Now, the theory of gravity involves something called a graviton, which hasn't been really discovered yet. They're still looking for it. So, in order to really look at the theory of gravity, we need something beyond this course, but not a problem. We can talk about the effects of gravity without really understanding the complete source of what causes gravity. But on Earth, the gravitational force acting on any mass close to the surface, that is, where you and I are sitting right now, will cause an acceleration of approximately 9.81 meters per second squared down. That means when you drop an object, in the first second it will accelerate from 0 to 9.81 meters per second. In the next second it would accelerate to 19.62 meters per second. Every second it accelerates another 9.81 meters per second. So 9.81 meters per second or per second squared. And we say negative because it's down. Now this is an average value because the Earth is elliptical in shape, and therefore around the equator the acceleration of gravity is different than at the north or south pole. And so for any questions though in North America that we tried using gravity, most textbooks, and including your diploma, will use 9.81 as the standard, all right? But just remember, that's an average value that's used in most textbooks, okay? So when we do kinematic problems that involve falling objects, the same four formulas come up, but we are given G, and we substitute that value of G for A in these kinematic expressions. So on Earth it would be 9.81. On the Moon we know that the acceleration of gravity is only 1.67 meters per second squared. That's why they have to sort of move around a little bit differently. They sort of do the hopping thing. So A would be 9.81 in the first kinematic expression. Notice in the second one there is no value of A. In the third one, A, if it was a falling object, 9.81 would go in there. And of course we use negative because negative indicates a downward direction. Alright? So A is 9.81, A is 9.81, A could be 9.81. Acceleration due to gravity actually changes as you increase your elevation, but you'd have to go very, very high before you notice the effects. So for any earthbound questions involving falling objects, we use 9.81 meters per second squared. So if we want to look at some extra practice in kinematics, there's no end of questions that we can ask, all right? And the more you do, the better you get. We usually start with these 5 variables. And of course, each equation has only 4, but of those 4, you'll usually be given enough information to know 3 of them, and you'll solve for the 4th. So that's part of the problem, is sorting out the information that you're given and then using it appropriately, figuring out which is best suited to give you a solution. So we use these 4 formulas or equations for uniform acceleration, and that includes acceleration under the effects of gravity. And then, of course, if we have an object that is moving with constant velocity or acceleration is 0, then we still have our v is equal to distance over time, or displacement over time. So these are the 5 equations that you've been introduced to in this course up to this point, and these are all found on your formula sheet when you write a quiz or exam in this or any other Physics 20 or 30 course. So when it comes to extra practice, you can learn a little bit by watching others do it, but the real way to learn is a hands-on approach. And this means trial and error and develop your problem-solving skills. Try not to make over and over and over. Once you've tried these following problems, then you can look at the solutions. They will be in small sections after this particular lesson is presented. Then you'll see the solutions offered one by one in the WebCT outline. All right, so it's important that you try these on your own. All right, only view the teacher solutions after you've tried these on your own. Then you should try all of the assigned problems here and in your textbook, and you'll find that the more you do, the easier this whole process becomes. But it is difficult at first. So the first example is a fairly simple one involving a motorcycle initially at rest, so you know VI is 0. It accelerates uniformly. A is 3.5. 65.5, that's D. And then, of course, they're asking what is the final velocity in both meters per second and kilometers per hour. The answers are there for you, and you can try this, and then once you've gone through this example, you can look at your WebCT, and the solution to this particular problem will be recorded as an attachment to lesson number 9. So continuing on, another example, a rock is dropped from a height. Of course, when an object is dropped, the initial velocity is 0. So we already know the initial velocity here is 0. It falls 15 meters. Which way is it falling? Well, it's falling down. Most people that are doing this kind of problem will make the 15 meters negative because it starts at the top, ends up at the bottom. That's a negative direction. Acceleration, of course, due to gravity, we just discussed that gravity is 9.81, but it's negative, so negative 9.81 meters per second squared would be your acceleration. So you already know initial velocity 0, displacement negative 15, acceleration negative 9.81, and then they ask, how long does it take? That's t. How fast is the rock moving when it hits the ground? That's final velocity. And then, of course, there's a sort of a tricky little question at the end, what was the average speed? Well, this one's actually quite simple. Once you figure out B and know the final velocity, the average, as we mentioned in an earlier lesson, is just the initial plus the final divided by 2. And this makes the point that the average velocity will be half of the final. All right, and that's an interesting point. You'll find that out as you go through these examples. And this one also, try it on your own, and then you can in a attached lesson. So the third example, a ball is rolled up a ramp. Draw a picture, and after 3.25 seconds reaches its maximum displacement. And of course that means that it's stopped rolling up. If it's stopped rolling up but it hasn't started coming back down yet, then you know at that point the velocity is 0. So at the highest point the velocity is 0. What was the initial velocity? What was the acceleration on the ball? All right, these ones are found, of course. You know the time. You know that at the midpoint, that is the 3.25 seconds, what's the velocity? The velocity at that point is 0. So you know that t is 3.25 seconds. You know that final velocity is 0. And you know the displacement was 8.15 meters. With those three variables, you can solve for the initial velocity, solve for VI, or in B, you could actually rearrange and find a different equation and solve for B. Try them. The solution will be shown a little bit later. And of course, the fourth example, a rock was thrown straight up from the top of a hill. All right, from a height of 15 meters, and on its way down past the point and release and hit the ground below. You ignore air friction, so you know what? You know that the acceleration of gravity is negative 9.81. You know the initial velocity was 11.5 meters per second. You also know, and this is an important idea, you also know that the displacement is 15 meters from the point of release, which is right here, to the point where it lands, which is right here. That distance from the, or that displacement from the start end is 15 meters. Which way? It's 15 meters down. So you know that the initial velocity is positive 11.5. You know that the acceleration is negative 9.81. You also know that the displacement during the entire trip, even though it went up for a while, the overall displacement from where it started to where it ended up is negative 15. So you have three variables. You can then solve using various formulas. You can solve for the final velocity, and you can also solve for the time of flight. So this is a good problem. A little more involved than the first three. Definitely one you should take a good look at before you look at the teacher solution. The next example, while riding in a Ferris wheel, a person dropped a candy bar from a height of 20 meters. Now in this case, the Ferris wheel is moving, then you know the initial velocity is given. In this case, in A, if the Ferris wheel was moving up at 8.5 seconds or meters per second at the time of release, what was the time of flight and the final speed of the candy bar? So basically what they're saying is, in A, as the Ferris wheel was moving up and the person dropped the candy bar from a height of 20 meters, what would be the information about the total trip of the candy bar? And of course, if the Ferris wheel was moving down, it's going to hit the ground a lot more quickly. Now, if you notice the solutions for A and B, there's some interesting things that come out of there. But of course, you're given enough information. You're given the initial velocity. You know that this candy bar is under the influence of gravity, so the acceleration is 9.81. You also know that from the point of release, whether it's going up or whether it's going down, you know that from the point of release to the resting point, the final resting point on the ground, is negative 20 meters. Whether it's going up initially or down, the displacement is negative 20. So you know three variables, and you solve for the fourth, which could be final velocity or the time of flight. All right, what is the time of flight and the final speed? So excellent question. Number 6, a rock is thrown straight up with a speed of 15.4. What's the velocity of the rock when it hits the ground? Well, that's an interesting one that we'll talk about more in the solution, but even if you look at the key at the bottom, it gives you a pretty good idea of what was the total time of flight. Interesting question to ask. One of the things you should do is, just by drawing a little picture, you can see that if this is the ground, then as the object goes up, then it comes back down. A couple of things. The initial velocity at the beginning is the same as the final velocity at the end, except one's positive and the other's negative. At the top here, the velocity is 0. All right, it has no velocity because gravity has stopped it. And then, of course, just for an instant, it's 0, and then it starts to become more negative. And of course, what's acting on this object, the rock? Well, the acceleration of gravity, which is negative 9.81. So knowing the initial velocity, knowing the acceleration of gravity, knowing that the velocity is A at the top, it's 0, or at the bottom, when it comes back down, it must be negative 15.4. You should be able to solve for all three of these questions in example number 6. So this is another typical and very good question. So last two examples. Example number 7, a motorcycle moving at 35 kilometers an hour accelerates 225 kilometers per hour in 3.75 seconds. How far did it travel, and what's the acceleration in meters per second squared? So you know the initial velocity, you know the final velocity, you know the time of travel, so you know three variables, and they're asking you to solve for the fourth. In the case of A, you're solving for the fourth, which is D. In B, the fourth, which is A. Now, one thing with this is you have to take those velocities, the kilometers per hour, and convert them to meters per second. Remember how we did that? To convert from meters per second to kilometers per hour, you multiplied by 3.6. In this case, what you should do is take that 35, divide by 3.6. That will give you your initial velocity in meters per second. And of course, do the same thing with the 125. Divide by 3.6. That'll help you convert to meters per second. All right, excellent question. And the last one is the skier initially at rest accelerates uniformly down a slope. The time of travel is 9.3 seconds. And what's the speed? What's the acceleration? Of course, you're given initially at rest, VI is 0. The distance that she traveled, 75.8. The time of travel is 9.3. The final velocity is one of those fourth unknowns, and also what's the acceleration? That can be a fourth unknown. You have to pick the right equation in order to do these.